Thank you.
Yeah.
Morning, everybody. Can you hear me in the back? Yes? Thank you very much. So we have 20 minutes or so, Lee, so I thought I'd take 15 minutes for the introduction. Is that good?
Okay. Sounds good.
Yeah. So this is one of my favorite posters, Go Do Epic Things. And I think I think the message hopefully today is I hope you all go forth and be awesome and do great things. And what I wanted to do is just share 2 minutes of how we all got here. I think we all have a story like this. This is my mom, and I lost her 20 years ago. And she said, I want you to focus on cancer, Scott. And then so I have this picture of me, and clearly one's better looking than the other. And I'm actually a head taller than my brother here. And many years later, he still has the same amount of hair, which is pretty interesting. And we basically decided to focus on cancer. And I really couldn't help, I'm a programmer, until I met this man, Dr. Leroy Hood. This is 2020, and I discovered next-generation sequencing. Once I discovered NGS, I realized maybe it's a programming problem. Maybe we could apply the techniques in AI to actually understand these patterns and maybe actually program cells. Crazy thought. And I met Dr. Hood, and he said, Scott, I want to do hyperscale AI with phenomics. And I hope you see today as he walks through phenomics, you'll start to understand many of us are taking a very similar approach, isomorphic, but seeing different parts of the lens. And Lee said in January, Scott, let's go get the band together. And then I saw, as I tried to find where is hyperscale AI that Lee talks about, and this is a paper that decided not to vote on the election, but said, you know, cats versus dogs, they clearly don't like cats. And what this is there's technology that allows us to generate cat videos, cat memes. And it turns out cat memes are incredibly powerful for cancer. Because if you look underneath a video, you get a score like you see on the left. You see audio, video, captions, text, characters, environment. It's like a video of life. If you can understand video and generate video, we're finding that the exact same technologies, the transformers, the diffusion models, AlphaFold, work beautifully with cancer. And it's allowing us to do things like the FDA is looking at programmable vaccines today, where on the upper left you see mRNA-based vaccines, where in green, that's the code for HER2-positive cancer, an antigen. If you put that into an mRNA, your body can activate the immune system and actually attack the cancer, and it's working in trials today. On the lower right, if you don't have a good immune system, we can program the tooltip on a heavy chain and actually create these basically T cells that can attack cancer for you. That's today in trial now. And if you look at this, once we realize and we can build an assistant in AI that can help all of us in oncology. This is from Apollo 8. We're going to have on Earth 2 billion AIs, where each AI today takes about 8 different NVIDIA machines, which is 5,600 watts. If we have that for ourselves, that's 1 billion of those, and 1 billion for robots, that's more power than the entire planet has today. So that's where we're headed. I can't thank you enough for all coming and helping me with this mission of mine and my brothers, and I think we all share some similar story. And with that, I want to introduce Dr. Hood.
Great. Well, it's a pleasure to be here, and I'm going to make a simple point in this lecture. Medicine is undergoing a fundamental revolution, and we all agree about that. I'm going to tell you exactly what I think is driving that fundamental revolution. So, individual data-driven health allows us to do 2 things. 1, optimize the wellness of an individual, and 2, identify early and prevent diseases, and that's what I'll focus on today. What I think is very interesting is data-driven health for each individual includes their genome and their longitudinal phenome, and in a moment I'll tell you exactly what that means. I want to make the point that in 2021, we created a nonprofit called Phenome Health, and that's driving this whole idea of data-driven health. And more recently, we spun off an Phenome Health AI technology company called Phenome, which I'll talk about at a little later time. So I'd like to discuss three different discussion points. So one, the idea of data-driven health, optimizing wellness, and especially early detection and prevention of disease. Two, the conjunction of data-driven health and its information, together with AI and together with clinical expertise, is going to generate in time the capacity for doctors to be domain experts in all areas of medicine. And then three, what is really going to be necessary to catalyze a fundamental revolution from our disease-oriented healthcare to one of wellness and prevention is a 1 million-person project over 10 years where we'll do genome phenome analyses. So in thinking about data-driven health, let me make three general points about the context in which I think about it. So, of course, the genome is invariant to a first approximation across life, and your genome specifies your life trajectory. And, of course, your phenotype is how the genome information is used. And the two most influential impacts on the nature of your phenotype are, one, your behavior, and two, your environment. And of course, the phenome is essentially any feature in a human that changes over time. And we actually measure blood analytes and gut microbiome and digital health for body and brain and a variety of other things to be able to generate the information. Now, the second point in this context, which is really important, is the imperative of using this information with a systems approach. And one fundamental idea that comes from systems biology is the idea that blood is a window into health and disease. It bathes all of your organs in the entire system. They can secrete molecules into the blood, and if you can quantify and read the origin of those molecules, you can make assessments about the health of each organ. And we can do that in an interesting, limited way. And of course, what this means is we can take that information then, and we can integrate those different types of information and phenomic measurements to generate the digital information. And we're talking now in the context of having set up a wellness company that extended from 2015 to 2019 and did genome and phenome analysis for 5,000 individuals and has to date generated about 30 papers in peer-reviewed journals, each of which gives us a view of what it is to optimize individual wellness or early detection and the possibility of reversal of chronic diseases. And of course, the second feature of systems biology are the biological networks that underlie normal and disease physiology and their dynamics if you have longitudinal information. And so these two features, blood being a window and the dynamical networks for both health and disease, are key aspects of the information we'll need to be able to feed to AI to get the useful creation of actionable possibilities that is going to be the foundation for optimizing wellness. And finally, of course, we'll use the tools of AI, and it includes machine learning, it includes knowledge graphs, which connect the data of an individual with the data of the medical literature, digital twins, which let us make probability estimates about the future in the context of different treatments or environmental or behavioral aspects. And finally, using large language models to deal in interesting ways with complexity. Now, data-driven health, as we'll see, really has three different phases. And one of the most important of those phases are the transitions. We're born in wellness, most of us. We transition multiple times to disease and back until the final stage of life. And of course, what is really important to note is the clinical signs of a disease occur long after the initial transition points can be detected. And in fact, for Alzheimer's disease, you can detect the early transitions 15 years before you can do the clinical diagnosis. And in cancer, we'll show you can easily do that 1 to 4 years before the clinical diagnosis. Now, a really important point in the context of disease-perturbed biological networks is from the transition point to clinical diagnosis, the networks increase exponentially in complexity. And that means if you start treating many diseases after they're diagnosable, your drugs treat symptoms and not fundamental causes. The real key is the early reversal at the transition point. And so you can see these three different aspects of health, wellness, transitions, and disease. We can deal with them in a data-driven manner in various ways. For example, with machine learning, we can do statistical correlations among different data types. And these lead to the medical literature and actionable possibilities that can be used to improve individual wellness or avoid disease. With Aravel, we generated more than 200 of these actionable possibilities. With the million-person project, we'll be generating tens of thousands of actionable possibilities, and to be able to deliver them to physicians absolutely demands the use of AI. Number two, we'll show you that we can detect these early transitions and get real clues as to how we go about thinking about early preventive therapies, and we'll talk about that in just a moment. And of course, dealing with disease itself, we're beginning now to take big data approaches to the longitudinal analysis of the 4 major chronic diseases so we can stratify the diseases and stratify the patients and their responses to these things. So let's talk about early detection and reversal. There are 2 approaches that we can use to do this. The first is assessing every 6 months the phenome, and in this particular case, hundreds of different proteins and so forth. And the changes in concentration of those proteins are the indicators of early transitions. And number 2 is the idea that we can use polygenic scores in populations to classify each individual with regard to their genetic risk for now hundreds of different diseases, including many different kinds of cancer. And if you have a high genetic risk and the right blood analytes, you then are poised at a risk point where we can begin, again, early diagnosis and a reversal. And I'll give you an example of each of these here. So in Aravel, we saw 167 transitions from wellness to disease, 35 were to cancer, and we actually took one of these, which we called Eve, and we analyzed blood draws prior to the clinical diagnosis out to a year and a half before or so. And what we looked at with regard to each of these blood draws were 9 disease-perturbed networks that were characteristic of stage 4 pancreatic cancer, which this individual had. And we showed in the first case, first earliest time point, there were no diseased biological systems. In the second, there was 1. In the third, there were 2. And in the fourth, there were 5. And of course, that means we have, again, an exponential increase in the number of biological networks. And what we were able to show in this case was that it's absolutely imperative for an example like this that you begin the preventive therapy early when it's easy to reverse. We looked at 9 additional individuals transferring to cancer. We found exactly the same thing, with the blood proteins being elevated anywhere between 1 and 4 years prior to diagnosis. And the really key point from a systems biology point of view was the proteins pointed to the disease-perturbed networks, which A, defined what type of cancer it was, and B, gave us a clue about where to start in simple preventive therapies. And the preventive therapies is really an interesting question that we unfortunately won't have time to discuss. So if we translate that information into biological networks related to pancreatic stage 4 cancer, you can see how beautifully exponentially increasing the complexity is and why we want to start at the very beginning. And remember, we've only analyzed 9 networks out of a very large number, so we would have to multiply those numbers all by significant numbers. Okay, so let's talk about the second approach, where we take polygenic scores and we determine your genetic risk. And I was fascinated in 2019 when there was an analysis done of some 400,000 individuals in the British Biobank with regard to a whole series of polygenic scores, and I list just one here for breast cancer. And what they were able to show beautifully is as the genetic risk increased toward the right, there was an increased susceptibility to disease. And what was really striking, if you replace the y-axis with clinical symptoms, you could show there was an exponentially increase of clinical symptoms resembling those that actually had transitioned to disease. So what we did next, and this I think is one of the most important papers we did, was to analyze 1,200 analytes in the blood, proteins, metabolites, clinical chemistries, with regard to increasing genetic risk in the Airville population of some 5,000 individuals. And what we were able to show, and we analyzed the analytes one at a time in that context, and what we were able to show for all 3 classes is that in general, of the 1,200, 800 responded to one or more of 54 different diseases where we had genetic risk. And the response was either a linear increase, a linear decrease of those chemistries. And where we knew the final chemistry of the disease itself, we could say the highest risk people had analyte compositions that mimic those that had always transferred disease. So they're poised at that point, ready to transition over, and that's exactly the time you can begin preventive therapy. But there is one other really important aspect, and we only have a single piece of data on this, and that is the question of when the analytes, your genetic risk is existent at birth. Your potential often expresses itself later in life. So how do we find out when that potential is expressed? Well, we'll be following each of those analytes as a colleague of mine did, a colleague that had 3 ancestors on the male side of the family that died of heart attacks before 50 years of age at enormously high risk for cardiovascular disease. he started taking his LDL cholesterol in his teens, and he found out all of a sudden in the mid-30s it shot up with no change in behavior, no change in diet, and maybe genetic. I mean, there are 3 reasons why it can shoot up like that: genetic reasons, behavioral reasons, or environmental reasons. But what was interesting is nothing would bring it down with regard to diet or exercise except statins, and they brought it down beautifully. So the question then is, when you put together high genetic risk with appropriate blood analyte profiles, you have a second approach to diagnosing disease very early and beginning the reversal. So let's talk a little bit about AI and healthcare, and I'll just make the general point. I think there are 3 really important things to stress. One is we have lots of different data types that can be integrated together, and the integration of a multiplicity of data types begins to recreate the enormous complexity of human beings. Number 2, we have very powerful tools for AI analysis, and we talked earlier about those. And of course, number 3, you need expertise in systems biology, healthcare, and the ability to persuade patients to do what's good for them, which is one of the biggest challenges in this endeavor. And then AI to then create a system that gives us very powerful tools that allow us to engage the 4 Ps of healthcare. I defined that in the early 2000s as the ideal healthcare would be preventive, predictive, personalized, and participatory. The first 3 are more science-oriented. The 4th is education and psychology and sociology. But AI enables, for example, with the predictive side, the discovery of what the genomic and phenomic analyses reveal, both with regard to actionable possibilities and potentially, in some cases, causal insights. On the preventive side, the engagement is really key, and we're now playing with AI agent-based chatbots that have experiences that will allow patients and later physicians to be able to query them with regard to the complexities of their own health data and appropriate actions. And of course, the scalability and the personalized thing, it delivers the individual health care. And again, remember, in the future, we'll have tens of thousands of actionable possibilities that need to be pointed, precise, and prioritized for each individual and delivered to the physician. And of course, on the 4th, participatory, being able to translate the complexity of medical analysis into language that, on the one hand, physicians can understand easily, but on the other hand, the patients themselves can understand and integrate is really key. So I think med-splaining is what Phenome AI is really going to push. The instantaneous access to data in the literature about where you should go with this patient and disease, optimizing from genome and phenome the best care for the patient, and explaining clearly what's going on with regard to simple decisions and decision-making allows the doctor and physician to work together. And the final point I'd like to make is I think this Human Phenome Initiative I spoke about, in a sense, is a second genome-like project that follows on beautifully from the first. And the idea, of course, is to take whole genome and longitudinal phenome analyses of 1 million patients over a 10-year period. And that will give us the ability to validate 3 things. 1, the health for each individual was enormously optimized and how it effectively did so. Number 2, if we can begin in a 5 to 10 year period to avoid chronic diseases through early detection and prevention, since they constitute 86% of the healthcare dollars of a $4.5 trillion market. There'll be enormous cost savings that in principle could go back to treating wellness at that point in time. And then number 3, and this is really an important point, we will be able to develop technologies that will allow us to take the complex data of multi-omics and impedance match it back against wearables. So in time, we hope most of the data analysis could be done with wearables at home mediated by a cell phone. And that has obvious implications about what's going to happen. So I'll argue that if we succeed with the vision of data-driven health and this million-person project that will solve the 5 major challenges of contemporary medicine today. 1 is the quality of individual health care. 2 is the aging population. 3 is the explosion of chronic diseases. 4 is racial inequities. And then 5, of course, is the exponentially increasing cost. All of those things, I think, could be managed by a data-driven approach that's shown here, and they'll really lead to 3 paradigm changes. Data-driven wellness and prevention, of course, lead to the idea that we can replace our healthcare today entirely driven virtually by disease with one that's driven by wellness and prevention. Number 2, we can democratize data-driven healthcare because it can be done at home and simply, not only to extend it to the US, but to, in time, underdeveloped countries where they do have cell phones and simple ways of treating this. And of course, the really critical point of all of this is having data-driven information from the genome and phenome of many, many individuals. And I predict within 5 years, we'll have millions of individuals that have been so analyzed. So this isn't going to happen tomorrow, but it is going to happen in the near future, and it's beginning to happen now. And it's going to be AI and phenomics that will allow doctors to be domain experts in the entire spectrum, across the entire spectrum of medicine, and deliver healthcare in a way physicians never could have delivered it before. The team that is bringing this vision to you, 2 of them are here. BJ Yurkovich is here and Jennifer Lovejoy, and both are associated with Phenome AI as well as with Phenome Health. So thank you for your attention.
Good morning. I was thinking I'd get through that before I got on stage, but clearly I haven't. Thank you, Dr. Hood. What a great talk this morning. I think there might have been a little bit of an order change because I was thinking that you would hear from a kid from Kansas, but instead you heard from a guy from MIT and now a kid from Kansas. It seems like it might have been a bit out of order. Either way, my name is Rick Ray. I work for Google Cloud based in Kansas City. Lucky for you, that's not why I'm here to talk to you. We started a foundation in Kansas City called the Supporting Kids Foundation. It's a grassroots organization based in Lenexa, Kansas, if any of you know where that is, founded back in 2009. The reason we started this foundation was about 16 years ago, our community saw firsthand what helping a family does that's dealing with childhood cancer. And one of the things that we've really learned from that to now is that no one budgets for cancer. We had a family in our neighborhood who experienced exactly that scenario. They received the devastating news that their child had cancer, and their son was only 5 years old, diagnosed with osteosarcoma in one of his knees. So his parents were handed this difficult decision to either amputate his leg or go to Miami, Florida for a trial procedure to do a pediatric knee replacement. The catch was, obviously it wasn't local, and the cost was going to be tremendous. When our community heard that this was taking place, a few of us put together a golf tournament, raised $13,000 or $14,000 in this golf tournament, and just basically wrote this family a check. And hopefully it would cover what the insurance didn't cover, as well as any of the travel and living expenses while they were there for the 3 or 4 weeks that they had to be there. So that's how the Supporting Kids Foundation was born. And I will tell you that that kid is now 21 years old, living a happy college life, still has both legs, and he's in full remission. So, with that being said, every year alone in Kansas City, there are 200 new cases of cancer. These families are receiving devastating news. As you can imagine, is paralyzing to hear it. Not only do they hear this news, but they have to start thinking about what are they going to do to help their child get better. And one of the things that we see a lot of in Supporting Kids Foundation is generally a parent will stop working, right? And it means a lot of time in the hospitals and a lot of time for treatments. And inevitably, these parents will miss work, right? And when you miss work, that's right, you don't get paid. When you don't get paid, you're not able to pay your bills, your household bills, just basic things like cell phones, car payments, whatever that might be. That's where the Supporting Kids Foundation comes in. The Supporting Kids Foundation helps pay all the bills that these families need, no questions asked. We're able to give money to them for, we've built onto houses, we've fixed cars, we've paid mortgages, cell phones, utilities, you name it. And unfortunately, we've even covered some funerals, which is unfortunate. Since inception, the Supporting Kids Foundation has helped over 900 families in the Kansas City area. We've raised over $4.5 million to date and given almost all of that money out to local families in need. The Supporting Kids Foundation currently gives out about $80,000 a month. I checked yesterday, and I believe that number is now $83,000 a month. And I think it's very important to know that our board is 100% volunteer-based. No one gets paid. If we were to take all the costs from our events that we have, we'd be able to give about 98% of all of the money we raise to kids in need. We work closely with 2 hospitals in Kansas City, KU Med Center and Children's Mercy. These hospitals facilitate and give us access to social workers that actually allow us the availability and need to find what these families do need via social workers. And in many cases, we lean heavily on them to understand which families need what and how we can help them moving forward. In many cases, one of the things that we found that we can really only give these families is a little more time. If you were to think of the time variance here, it's considerable. We've seen cases where families are dealing with children that go into full remission, but then we see families that have a month, days, weeks, maybe a couple hours left with their child. Ultimately, the Supporting Kids Foundation is providing them a little bit more time. So, I challenge you to sit here and think to yourself, if you had a child dealing with this, and you had a couple days or a couple hours left, what is your true value of time?
My name's Brian Weber. I lost my little girl, Lucy, to brain cancer. In fact, this coming November 20th will be 10 years since we lost her. This might be kind of tough here. But, in 2010, Lucy started getting sick. We noticed a lot of things. It was, incredible fatigue, just some stomach ailments and things like that. We took her in, and after finding some little stuff here and there, they wouldn't give us a real diagnosis of what was wrong with her until they finally said, well, okay, we need to do a brain scan on her, and that's when they found a large brain tumor with a cyst in her brain. They gave us that diagnosis, a couple days before her first birthday. She spent her first birthday having brain surgery. You get that news, and we've all heard the stories of what it's like. You never brace for that, you never really fully prepare for something like that. You get that news and, it takes your wind away, just knock the life out of you. One day in particular, I remember being at the hospital with Lucy, and Bev was with our other daughter, Lily. Bev was at some thing with one of her friends, I had no idea what it was, but she called me later that night saying, hey, don't worry about, work as much this month, be there with Lucy. I just met some incredible people, and they just gave us a check. When things like that happen, it restores your faith in humanity. I mean, the financial part, yes, that's fantastic. I mean, there's a lot of people that really, 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 truly need that. These kids really, really, truly need that in different ways. They need that energy. They need that care from their parents. They need someone to be there with them. They can't fight this battle alone. I love how SKF comes in at that point and says, we're here to help you through this part, because all the other foundations, they help out with the research, and once that diagnosis happens, though, they help treat the illness. They don't treat the child. They don't treat the patient. They don't treat the family. And a child going through cancer treatments, chemo, radiation, surgery, all this kind of stuff, I mean, they are scared out of their minds. They don't know what's going on. They don't know from day to day if they're going to make it. They don't know why. The only thing they know is what comforts them. And as a parent, being there with your child while they're going through that, I mean, you have to, as much as you want to just hold them and squeeze them and say everything's going to be fine and hope it will be, it doesn't work that way. So the only thing you can do is comfort them and be there with them and look them in the eye and say, I'm here for you. This November 20th, it'll be 10 years since I buried my daughter. When you put those words into it, I want people to understand that. It's serious stuff. And what SKF did in that time was they bought us time. That's time I'm never going to get back. If I didn't have that time with my daughter, and I would have taken it for granted and said, oh, it's going to be fine, I never would have had it back.
So I've heard that story, I don't know how many times. It never gets easier. And we hear a lot of them, unfortunately. There are a lot of folks that are going through this right now, and it is a sad thing that I'm hoping a lot of you folks can help solve. In closing, if there is anyone interested here, or anybody that knows anyone interested in starting a foundation similar to the Supporting Kids Foundation in your area, send us an email. We would be more than happy to help get you started or help them get started. For others, if you're interested in making a charitable donation, the Supporting Kids Foundation is a 501c3 organization. Obviously, all your donations would be tax deductible. And you can scan the QR code on the screen, follow to the website, and you can donate whatever you'd like. Thank you very much. I appreciate your time. I hope this symposium is great today. Thanks.
And is there a laser as well? Oh, yeah. Okay, good. Good morning, everyone. It's a pleasure to be here. I will talk, well, just a second. Yeah, I will talk about resistance in cancer and how we could use whole genomes to analyze those. Here are my disclosures. We work with Google to scale our computation and do things kind of in the cloud. Also research funds from IBM and Ultima Genomics and different patents. So I would like to start with kind of some definitions. We're talking about AI here, but what is AI? AI, if you look at the definition, it's the study and development of computer systems that could copy intelligent behavior of humans to make decisions, to learn from data, to reason, to do pattern recognition. And machine learning is a type of AI that uses a lot of data, large amounts of data, to learn without coding the actual rules. It's just using the data to learn the patterns. And statistics is a branch of mathematics that is about collecting data, analysis of data, interpreting, and also making sense of large amounts of data. So AI and machine learning and statistics are all in the same kind of continuum. So I think it's important that you kind of put AI in this kind of context of statistics and machine learning. And all of these use data and machine learning, AI, and statistics algorithms to have intelligent behavior, like making the right decisions or discoveries. So I want to talk about cancer today, and this is kind of the life history of cancer. We all start from one cell, the fertilized egg, that already contains the potential risk alleles or risk genes to develop cancer, like Dr. Leroy Hood talked in the morning, this kind of earlier, about this kind of potential risks. But then cells divide in the body, and every time cells divide, they accumulate mutations. There's DNA damage occurs. A lot of the DNA damage is repaired by repair mechanisms, but then some damage is not repaired and becomes mutations, and they are carried on in the lineage of the cells. But this is not cancer yet. There's just mutations in different cells. How can I use the laser here? Yeah, I can't. But then sometimes occurs an event that is a driver event that increases the fitness of the cells, and the cell starts to grow and grow a clone of cells faster than the neighboring cells. So either they grow faster or die slower. Then this is not cancer yet. This is a growing clone. We are all full of them, and as we age, we get more of those clones in our bodies. Then at some point, the immune system might identify this clone because there are already neoantigens presented, and the immune cells start to attack the cancer cells. And then could be another driver event that evades the immune pressure. Essentially, every cancer is a failure of the immune system in most cases. And then there could be another driver event, another mutation that further increases the fitness of the cells, and they continue to grow and take over the population of the other cells. These are these red dots. And then there's this, what we call the last clonal driver event, where all the cancer cells eventually are derived from that cell. So what that means is that all the cancer cells share mutations that are accumulated all the way from the fertilized egg until this last clonal driver. But then cancer continues to evolve with subclones and other drivers, and then it's diagnosed. And then treatment is given, and then most of the cancer cells die, and maybe some don't die because they have mutations that make them resistant to the treatment, and then they continue to grow, and then there's a recurrence of the disease. And then there's additional drivers, and there are drivers of resistance that actually increase the fitness of the cells under the therapy pressure or the therapeutic pressure. And cancer precision medicine is all about understanding this life history of cancer, from your risk alleles at birth to what are those driver events and pathways that change during the evolution of cancer, so we could give the patients the right drugs to prevent this or kill those cancer cells or prevent the progression. And there are many drugs that are given today, as you can see, based on different events throughout the life history of cancer. At least these are the cancers that we don't cure. Luckily, some cancer we do cure, and there's no recurrence of the disease. So there are many questions that we ask. For example, how do we discover those drivers? How can we identify the cell states of the immune system? What are those? How does the cancer cells evade the immune system? Can we predict who will develop cancer? How can we find the combinations of therapy that would actually prevent resistance from being created? All of these questions, to answer them, we need data. We need data, which uses then statistical tools like AI, machine learning, or more classical statistics to make discoveries and answer these questions. So this is kind of the kind of what the types of data we generate through the lifetime of patients. There's diagnostics of the disease. Maybe the cancer is resected, so we have the tumor cells. And then we could have blood drawn during the different times of kind of the life of the patient. And then in research, we're actually using sometimes rapid autopsies to get samples from multiple sites on the body. And then we use all this information to make better clinical decisions, but also to support research to answering all these questions. And there are a lot of data. There's clinical data, molecular data. There are prior knowledge, like the literature. And we need to integrate all of these data to make the right decisions and make further discoveries. So one thing that we used AI in cancer research is actually to find all these genetic events in the cancer genome. And this is more complicated than finding germline events, which happen in either homozygous in all your DNA alleles from mom and dad, or heterozygous in one of the alleles. But in cancer, it could appear in a small fraction of the cells, because when you take a piece of the tumor, there are normal cells and tumor cells. So you could actually have the evidence for the mutation only in few reads when you sequence the DNA. So we've developed many years ago algorithms that use AI or statistical techniques to find these mutations in these somatic mutations and then identify single base changes or insertions and deletions or translocations or copy number changes, et cetera. And what you could see is that you need deeper sequencing to find these rare mutations. So if it's what's called allele fraction of 0.05, you'll need tens or hundreds of sequencing reads covering the mutation to find the mutations. Now, how do we find the drivers? In order to find the drivers, we can't use one patient. We need to use many patients to find out what are the recurrent events. And over the years, we've developed many tools that look at recurrence events, recurrent mutations in the gene, or recurrent copy number changes, or clustering of mutations in the three-dimensional protein structures, to find evidence that these genes or regions of the genome or proteins have more mutations than you'd expect by chance, because there are mutations all across the genome that are just random, these passenger events. We look for the drivers that really gave the fitness advantage to the cells. And you could actually calculate this power calculation. How many patients do you need in order to find drivers that appear in 10% of the population, 5% of the population, 2% of the population, et cetera? And it depends on the background rate. Some cancers have many more mutations, like melanoma, that is due to the sunlight. So these we need maybe 5,000 of patients to find drivers in 2% of the patients. In other cancers, you need fewer patients, but we need thousands of patients in each cancer type. For example, recently, we studied the chronic lymphocytic leukemia with 1,100 patient samples or tumor samples, and we were able to find drivers that we couldn't find before because we had more patients, so we could find drivers that affect 1%, 2%, 3% of the population, which these percents are important because there could be drugs that affect these pathways or these genes that could be given to 1 or 2 or 3% of the population. But now we're looking at drivers of resistance, not just the drivers of primary tumors. So how do we study resistance? We take a sample before treatment is given and a sample after treatment is given, and we look at the differences in mutations between before and after. And then we apply the same statistical tools on all the mutations, but only the mutations that are found in the post-resistance compared to the pre-treatment. The problem is that patients typically don't get a biopsy of the tumor after they become resistant to therapy. So in order to address that, we developed a procedure or a method that takes cell-free DNA that is shed by cancer cells into the blood, and detect how much DNA from the cancer cells are in the blood, because most DNA in the blood is not coming from cancer cells. We could estimate this fraction, and if this fraction is above 10%, we could do whole exome sequencing or even whole genome sequencing of the cell-free DNA. Then we still need hundreds of patients of these pairs. So we asked ourselves, how could we actually reduce the number of patients? In order to reduce that, we actually monitor patients over time, not take individual sample after treatment. We take as the treatment is given, and we could follow the clones that are growing over time. And finally, we could use in research mode rapid autopsy, where we take multiple samples from the same patient to really study the evolution of different clones within the body, because we are focused on the clones that are growing rather than the ones that are dying under the therapy. So how can we study multiple samples from the same patient, either in the second or third mode of collecting samples? We need tools that use statistical approaches. And for example, here's an example of five samples from the same patient. And each line here represents a clone of a group of mutations that occur at different fraction at different samples. And we detect that by a kind of advanced clustering method of the different allele fraction across these samples. And then we could build a phylogenetic tree. In order to do that, to combine these different clones into a phylogenetic tree, we need a statistical tool, a Monte Carlo method, that essentially tries all the different trees that could fit the data and finds the most likely tree. And then we could take each sample and ask, well, what fraction of the cells belong to each branch in the tree? So in order to find drivers of resistance, what it turns out that it's actually more powered statistically to look not at individual patients, but look at individual branches in the phylogenetic tree, because the same patient develops multiple mechanisms of resistance in different clones in the body. So we could use from one patient, there could be sometimes 5 or 10 different subclones. Each could develop different resistance mechanisms. And then we could essentially use from one patient 10 individual independent readouts of resistance. So when we did that, we studied breast cancer, and we found the most likely resistance mechanisms, mutations in this gene called ESR1, which is the estrogen receptor. And indeed, that was known as a resistance mechanism to anti-estrogen treatment, which breast cancer patients get. But the second gene, KMT2C, was not known to cause resistance. And indeed, we actually then tested in the lab. We created these mutations, this knockout of KMT2C in the lab in cells, and were shown that it is resistant to the therapy. So this is how we could find resistance mechanisms. But now the other part of my talk is to talk about how we could use whole genome sequencing to even answer this question in a better way. So you all familiar with this graph in the drop of sequencing costs over the last 2 decades. And this is really a miracle, and that's much faster than the Moore's law that the circuits and computers become faster over the years. And specifically in the last year, multiple companies announced a significant drop in sequencing cost after a plateau of a few years. And for example, we're working with one of these companies, Ultima, that announced that it will drop to $1 per gigabases, which is equivalent to $100 for a whole genome sequencing at 30x coverage. And even just that announcement caused Illumina to drop the price to $2 per gigabase. So that's great for us in the research and in the clinic. And that enables us to do a lot more research of the cell-free DNA and sequencing of the cell-free DNA, of the tumors, of RNA and the single cells, et cetera. So the field is really transforming with the cost of sequencing going down. So we've developed a pipeline and to analyze data, both Illumina data and this new kind of Ultima genomics data, and develop tools for doing pre-processing of that data to enable it to go into the same pipeline of calling mutations and copy number changes and insertion, deletion, et cetera. And that is, we build this on top of the Google Cloud. So I want to give you a bit of a kind of how this Ultima sequencing kind of works. So it works very different from Illumina, where you flow these kind of A, T's, G's, and C's in 4 different colors to read out the bases. In the Ultima, you flow A's only, and then G's and C's and T's, one after the other, and you measure the sequence based on the intensity that you get, because you don't use these terminated bases where you call one base at a time. If you have 4 bases at 4 A's in a row, you would read a bigger intensity rather compared to 1A. So that makes actually the reagent cheaper, but also what it causes that you could have more mistakes. Or if you have, let's say, 7 A's, you could say, well, I'm not sure it's 7, maybe it's 8 A's or 6 A's. So this is what's called homopolymer indels. So that's more noise of that type. So we've developed an AI-based method to improve the quality of the sequencing data from the raw sequencing data that you see on the left to what you see on the right. There are 2 mutations there, or SNPs, that are real, that you see those orange and green lines, but all those little insertions and deletions are actually noise, and you could see that we could really clean the data. So there are existing tools that use AI to call somatic mutations. Some were actually developed in Google, but we use a different approach. The approach that we use is to correct the reads themselves, to essentially generate a new sequencing data that is a high-quality data from this Ultima approach. So let me give you a bit of background how we call variants. So if you look at the genome, sometimes you could see SNPs. Those are in blue there. These occur in the germline of that patient inherited from their parents. Somatic mutations look like these orange ones, that there's a pileup, a few reads that support these mutations. And all the sequencing noise are these red speckle there that typically are, for example, in Illumina data, they're mostly independent. So that's kind of independent noise. So that's will determine how you'd find them, what would be the noise level or noise floor of finding the mutations. But in Ultima data, it's different, because you could have like these red ones in the middle. You have correlated noise, because if it's a homopolymer, for example, you have the same mistake in different reads, and that would cause us to mistakenly think there's actually a somatic mutation there. But that means that the correlated noise means that actually we could build a statistical model to predict this noise and then correct for it. So we actually developed an attention-based language model to translate the error, the noisy sequence to the true sequence, essentially the reference genome. And we teach this, like translating from English to French, we're translating noisy sequence to good sequence. And then we apply that on the sequencing data. And I could show you here, the lower part is the Illumina, the middle part is the Ultima raw sequencing data, and the corrected is on top. And if you zoom in, you could see that in the middle one, there's the insertions or deletions in the middle one. You could see the pileup of deletions. But when you go to the top one, you see that it's cleaned because this is noise. You could see also on the right side another one of these in deletions that are cleaned. But there are other mutations, like the orange one, that is not touched, and we could actually call these mutations. So what we could do with this technology now is that we could, instead of using whole exome sequencing data, we could use whole genome sequencing data, and we call many more mutations, because the exome is only where the genes are, which is roughly 1% of the genome, to the entire genome, which is 100 times more. And we can, instead of calling 140 or mutations from the exomes, we could call nearly 10,000 mutations in the genome of every sample, and you could use that to build much better phylogenetic trees. So if this is the exome phylogenetic tree from a patient that we had 6 different or 7 different samples from the patient, this is the same tree the same patient, but the tree with whole genome sequencing data, that we could see that the backbone of it is the same as we saw in the exome, but we find many more branches, and then we can find many more mechanisms of resistance that we couldn't find when we had the only exome data. So I suggest that we start thinking about whole genome sequencing on patient samples, going from not only the diagnostic sample, but also the cell-free DNA and other biopsies that are taken over time. And also, if we could have more, for research, more rapid autopsy, it will really enable us to find drivers of resistance, which could help us identify what are new drugs that could avoid resistance, or combinations of drugs to avoid resistance. Oops. What is that? That shouldn't be here. OK, that's it. So here I want to thank all the people that were involved in these studies and the funding sources, and of course the patients and their families that contributed samples and data for research. And I'd be happy to, maybe we'll talk later about questions, yeah. OK, oh. I don't need this.
I'll sit on this.
You choose wherever you want.
Yes, I'm going to sit here
Okay.
based on my speaker. So good morning, everyone. My name's Andrea McGonigle, and I focus on the pharmaceutical industry for Google Cloud. It is my joy to interview and sit down with the fireside chat with Gaddy here. Gaddy's one of my key customers, and I think you're very humble. You didn't even introduce yourself or give the background, so I'm going to give a little background on him. Gaddy Getz is a prominent figure in cancer research, particularly in the field of cancer genomics. He is a professor of pathology at Harvard Medical School and a core institute member at Broad Institute of MIT and Harvard, where he directs the Cancer Genome Computational Analysis Group. In 2023, Gaddy was named Precision Medicine World Conference 2023 Luminary Honoree for AI and Data Science. So I say if we were in the World Series, he would be an all-star player, by no doubt. And he has some key contributions, which he talked about today, and we're going to dive a little bit deeper in them. He pioneered using widely used tools for analyzing cancer genomes, which we've seen today. He identified new genes and pathways involving different tumor types. And he contributed to the understanding of mutational signatures and tumor evolution. And one of his passions are advancing the field of single-cell analysis in cancer research. So really thankful to have you and your thought leadership here today.
Thank you.
So let's get into some questions. When you and I first talked, one of the things that kind of jumped out at me is you said, we talked about this problem, and you said, we don't have enough data. And I thought, what? That's not something I would have expected. Can you expand on that?
Yeah, absolutely. So as I showed earlier in this graph of the power to detect drivers, we need thousands of samples from each tumor type. There are hundreds of tumor types of subtypes. We need hundreds of thousands of tumor genomes. We only have TCGA has 11,000 cases. The pan-cancer analysis of whole genome, a huge international effort, was 2,500. We need 10 times or even that, or whole genomes. We need kind of 20 times this amount of or more than that, 40 times the amount of these data. We need more patient samples. How do we get those? Either patients could contribute their own data or samples, or hospitals or clinical kind of teams that could collect those samples. We need to obtain samples, not only diagnostic samples, but also after resistance to different therapies. So we need a worldwide kind of effort. Most samples today either are diagnosed in diagnostic companies. They have a large amount of samples. They are typically owned by these companies, the data for them. I would argue sharing more of these data so the entire research community could leverage those samples and learn about what drives primary tumors and what drives resistance And so we need the help of all of you here and to collect those samples and make them available for research.
Great, great. That's great insight. Thank you. You've been involved in massive projects like the Cancer Genome Atlas, the pan-cancer analysis of the whole genomes. How can AI help us analyze and interpret these data sets that are generated by these projects effectively?
So, great question, thank you. These projects generate multi-omic data, different types of data, whole exome, whole genome, RNA-seq, proteomics, methylation. We need to integrate all these data together. AI is good at that. We're already using AI, as I just showed, in different aspects of calling variants and then finding those drivers, recurrent events, building phylogenetic trees, et cetera. But as we said in the previous sentence, we need this is just the tip of the iceberg. We need a lot more data, and there we need more AI. AI needs data to train. The reason that large language models work is because they have all the internet of text to learn from. We need a lot more data to learn from that to really understand what are the patterns, what are the common patterns, what are the dynamics of these patterns, how they change over time. So I think the key is to generating more data and also using AI to study the integration of all these data types together.
Excellent. You talk a lot about single-cell analysis and the tumor microenvironment. Can you just ground us, like what that means and how you see AI helping and moving that forward?
Yeah, absolutely. So I'm sure most of you know, but there's a revolution that happened in the last decade, I say, of starting to be able to analyze individual cells. Starting from RNA from individual cells, now we could also DNA and different modalities of DNA, and really starting to build these phylogenetic trees of individual cells. That's a lot of sparse data that AI could be used to understand and how the dynamics of the cancer changes, how the immune microenvironment changes around the cancer cells, different types of immune cells, how the immunes in the blood could tell us something about what's going on in the cancer. So a lot of data that AI could help analyze and find these modules, the biological modules that happen in each one of these types of cells.
Excellent, excellent. Good. Given your extensive experience in cancer genomics, I want to think more future. When we look 5 years out, 10 years out, where will we be? What's your thoughts? How will that fundamentally change?
So it's a great question. It's not easy to predict what will be in the future. But I think that with the drop of sequencing cost, with the technologies like spatial transcriptomics and proteomics, and the ability to collect blood over time, we will see this replacement of pathology, which is looking at these slides today without a lot of information in them to really understand what is the expression and what is the DNA in each one of those cells with how they're related, the cancer to the neighboring cells, the immune cells and the non-immune cells and the cancer cells themselves in a spatial organization. So that's from how we will change pathology, and image analysis. AI is kind of clear, important in that. And that together with the genome of the cancer and following the patient over time, understanding, is the cancer cured? It's something called minimal residual disease. Is the patient, do they have still cancer in their body or not? Is there a clone that is starting to grow, and therefore we need to change treatment to something because that is resistant to the current therapy? All this I think will change in the next 5 to 10 years, where pathology will change and patients will be monitored over time to really understand how their cancer behaves to their therapy and how to switch therapy to avoid the growth. And of course, in early detection, again, as I said, DNA is shed into the blood. There are other proteins in the blood and other things that could be measured, circulating tumor cells that could be measured and identify cancer early. And that, again, will use AI to analyze all these data, the sequencing data, the protein data, the RNA, et cetera, and that's where we will be in the next 5 to 10 years.
That's great. That's great. I think for so many people who are affected by this, it's a great vision, and people want to be there and see that happen. So thank you for all your work there. I think that last question was more future 5 to 10, and you talked a little about what we can do from a data aspect, but what do you think, like today, after we leave, what can we start doing? Like, what's your vision for how do we start working on this problem right away?
So I would say combining efforts of many groups to bring, as I said, data together, generate more types of data, and in a systematic manner across more patients, with the understanding that we want this data not just to make the decision for the patient today, because we don't need all that information to make the decision about today, because we don't have enough drugs and not diagnostic tools, et cetera, but to collect data to do research and have a learning system that we could learn from the patients that are today how to better treat the patients of tomorrow.
Sure, yeah.
And that is something that can be done today because the patients being treated today. So we could measure them, generate data, think of how to share the data in a responsible way with researchers, how to allow patients to donate their data to research. That we could start doing today, and there are efforts going on to do that, to start to do that, but not large enough, because we should leverage the millions of patients around the world of cancer to learn how to better treat or new directions of treatments of patients in the future.
I agree, and I think events like this, where we're all coming together to really double click on this problem, think about what we can bring to the table. Gady, I want to thank you for sharing your thought leadership with us, and really excited about what comes out on how we work together and begin solving this. Thank you, everyone.
Absolutely. Thank you, Andrea.
Thank you, Gady.
Well, good morning. I'm Charlie Fuchs. Oh, thank you. I need a clicker. I'm Charlie Fuchs, and I lead global development in hematology oncology at Genentech and Roche, although I have a number of connections here in Boston. In fact, I spent the majority of my professional career here, so I really appreciate Bill and the team at Google Cloud inviting me to be present at this terrific meeting. I think that that what we're hearing from Dr. Getz and others is the power of artificial intelligence and machine learning to transform the way we deliver care, the way we conduct research, and ultimately deliver better, more effective treatments and cures for patients with cancer at a much faster pace. But I think it's worth pointing out the fact that healthcare, historically as an industry, has not been at the forefront of the IT revolution or artificial intelligence. As this graphic from a number of years ago points out, as you can see, healthcare grew at a rate considerably faster than the US economy, which is no surprise in terms of real growth. But much of that was reflected in the growth of the workforce. As you can see, it led in terms of employment growth. But I think what's particularly important to realize that because healthcare really did not embrace information technology as much as other industries, despite that considerable growth in workforce, healthcare lags behind almost last in labor productivity. And I think it really is the power or the lack of use of this power in our field. We know, for instance, in the retail business, right, and other industries, every customer encounter is put into actionable data. And we clearly need to see these opportunities because for the most part, the introduction of information technology in healthcare and healthcare delivery has been largely converting paper records to electronic records and creating systems that enable more effective reimbursement and billing. And the opportunities are considerable, right? That we can make data collection easier and better. We can turn data into actionable information. We can leverage all of it to improve quality and experience. And we can forge new operating and business models to make healthcare cheaper, faster, better, more effective, and ultimately deliver the care that patients need in the best possible manner. As a potential end user of these technologies, I've had a journey that has spanned the gamut of the healthcare sector. I started my career as a practicing medical oncologist while at the same time conducting research, leading a laboratory, clinical research, epidemiologic research, as well as translational research. In the last decade, I was privileged to lead the Yale Cancer Center and Smilow Cancer Hospital in New Haven, Connecticut, along with its 16 outpatient centers across the region. And in 2021, I was privileged to be invited to lead hematology oncology drug development globally for Genentech and Roche, and really have an opportunity to pursue my passion, delivering new therapies for cancer patients in need. But, you know, as I mentioned a moment ago, my journey started right here in Boston, down the street at the Dana-Farber Cancer Institute, which was then and is now a world-leading center in cancer care and cancer research. And I really had the privilege of getting my training and my early career there. But I will tell you, having started in the 1990s there, 1996, a long time ago now, was a tragic and pivotal moment in the history of this institution. And it relates to how we did care. Namely that, how did we order chemotherapy? We hand calculated the dose based on a patient's height and weight. We hand wrote the order in a paper record that was then given to the pharmacist who prepared the drugs and then handed to the nurse who administered the therapy. And that was not just the routine at Dana-Farber, it was the approach across oncology in the US and worldwide. It was the way we delivered care. But unfortunately and sadly, there are consequences to that type of process. Namely, in 1996, 2 patients were overdosed with chemotherapy, and it was a tragic event for those patients and for the families that were affected, and led to a dramatic upheaval at the Dana-Farber and frankly for cancer care in general for those of you who were involved in oncology at the time. Clearly, we needed to find better systems, better processes, because this cannot occur. And I had the privilege to work with the new leadership at the Dana-Farber at that time to come up with systems to ensure that an event like this never happened again. And part of that was the introduction of computerized physician order entry, sort of, you know, obvious now, but was not routine back then. And through that system, other processes in terms of how chemotherapy was mixed and how nurses administered and other checks and balances, we ensured that using the so-called artificial intelligence of the time, that patients got the right therapy and the right dose and at the right time, which is what every patient should expect from us to ensure that the best care is delivered. And that process continues to be iterated. This is a recent publication in Nature Medicine in which natural language processing has been used at retail pharmacies and other outpatient facilities to ensure that patients are given an accurate prescription and that it is easily interpreted by the patient of when and how to take that therapy. And what also happened with the introduction, the widespread adoption of chemotherapy order entry and just computerized medicine order entry in general, was the introduction of widespread of electronic medical records, which in other circumstances, was legislated by the Affordable Care Act in certainly the United States for good reason. And we, I think, all believe that the introduction of electronic health records had enormous promise to improve processes and change the way we deliver care better, faster, cheaper, and safer. It obviously has the potential to improve care delivery, to improve documentation and reimbursement, to enhance security, to improve communication between the doctor and the patient, between healthcare providers, to improve the application of the general public health so we can monitor across systems, and also, and importantly, to create efficiencies and reduce healthcare costs. But I would suggest that that potential promise of electronic health records, even today, has not been properly realized. Namely, those systems, forgive me for saying, I think were designed not as how we deliver care, but how do we ensure proper and accurate billing and reimbursement, which is vitally important, but it creates systems that have, I think, suboptimal, perhaps even poor usability for healthcare providers. It puts an enormous burden on the providers in terms of administrative and clerical burden, and it as well requires them to spend excessive time entering in those electronic health records, much of which you'll find out healthcare providers are doing at night because they don't have time during a busy clinic day. As well, I think to the disgruntlement of all, because you're working so intently on the computer, it diminishes the healthcare provider-patient interaction. And probably no less importantly, there's ample evidence that these systems are contributing to the growing phenomenon of healthcare provider burnout. But in fact, there are opportunities to change this trend. Namely, one can improve the usability of these systems in terms of tailoring the systems not for billing and reimbursement, but how do we improve the way we deliver care to a patient, trained specifically for the practice, for the specialty, as well to do research on what are the stressors from these systems on providers and patients so we can overcome those things. To use, of course, natural language processing in order to simplify documentation, to convert the entire encounter into structured data to improve care and enhance research. And ultimately, we know you can leverage these technologies to create efficiencies in care delivery, to improve the education of providers and patients, and improve decision-making, and ultimately to enhance clinical, translational, and population research. Beyond that, I think the power of electronic health records can really deliver medical knowledge in real time. This is an interesting observation that I saw recently in the New England Journal, namely the doubling time of medical knowledge, which was 7 years in 1980, and now is under 100 days, putting an enormous burden on healthcare providers to keep up with the growing complex landscape of what we know about medical science. But in fact, electronic health records have, of course, the ability to deliver that appropriate medical knowledge in the appropriate context in a timely manner when you're seeing the patient with that specific problem, improving patient care, improving the experience for the provider, and in fact, we think probably improving the outcome ultimately for patients. There have now been a multitude of reviews on the power of this technology and how it could potentially improve healthcare delivery. This is one such recent review from the New England Journal. And the review covers sort of the range of applications from the more consumer-facing, such as personalized patient outreach or identifying patients who should be identified for outreach, to more back-office administration functions, such as claims and reimbursement and financial management, all of which the range is important and powerful in what these systems can do. On the latter so-called back office function, for which technology is being applied, the fact is that reimbursement and revenue cycle management, having run a hospital, is vitally important, because at least in the US and to a large extent worldwide, healthcare organizations operate on a razor-thin financial margin. You really have to make sure that you get reimbursed for all the care that you deliver to keep your facility afloat. And the problem is that as much as 10%, if not more, of claims, reimbursement claims, are denied. As we know, 85% of those denied claims are avoidable. And that contributes to costs to the patient, the provider, the healthcare center, the entire ecosystem. So what is emerging are the ability of AI to create predictive analytics, to understand what are the characteristics of denied claims, and to actually implement changes before the submission so that you don't have the cost and the headache of having to overcome a denied claim. As well, having automated prior authorization. For those of you who are in the delivery of healthcare, you know this is the bane of existence for healthcare providers, calling up to get approval for a complex test or procedure, listening to Muzak for a few minutes while you're waiting for somebody to get on the phone to talk to you about that approval, and then potentially being denied. And this is not what physicians and nurses and healthcare providers went to school to do. And it's not what patients deserve. As well, payers can use these systems to automate claims adjudication, reducing the time and effort and pain of their administrative staff and medical staff in deciding whether to pay for the particular procedure. As well, these technologies can apply, of course, to the delivery of care in a number of ways. Namely, as I mentioned, using natural language processing to take the data, all of the data from the patient encounter, from the tests, the imaging, the lab tests, and actually create excellent documentation to cover what we know about the care of the patient, to enhance billing documentation, and as well to create structured data that can enable care delivery, care improvement, and clinical and translational research. As well, these systems can be used to figure out how we optimize use of the facilities, the operating room, the emergency room, the hospital, the clinic facilities, to improve diagnosis and screening, decision-making, risk assessment, patient monitoring, care pathways, which are critically important to ensure quality and safety and efficiency, and also to improve access of the patient to the health system, to improve their experience, and most importantly, to improve quality and safety. Of course, there's challenges to this. Healthcare is, I think those of us in healthcare would admit that we're fairly risk-averse beings in terms of introducing new technologies. And the problems are, considerable. One is we work in healthcare organizations that have unstructured, very heterogeneous data sources across a variety of origins, which make it hard to ultimately put this into action. There are costs to these introductions, which are not trivial. There's regulatory requirements. We have to make sure whatever we do, we ensure the privacy of the patient. There's the liability risk, right? If these technologies are going to influence decision-making, there's the potential for liability. We also have to make sure there are no unintended biases, particularly if they might disproportionately affect underrepresented minorities or groups that are not easily incorporated in the healthcare system. And then no less importantly, I think healthcare providers, patients, advocacy groups may have issues of trust. Can we ensure that these technologies, if they're incorporated into care delivery and decision-making, that they'll do right by the patient? It's probably easier, and we're hearing some of it, about applying these technologies into medical science and medical research. And during my time here in Boston, I had the privilege of working with these extremely large prospective observational studies of nurses and other health professionals in which over the course of decades, these individuals who were enrolled at the point that they were relatively young and healthy provided regular updates on their diet, their lifestyle, their medical history, their medication use, their blood samples, tumor specimens, tissue samples, anything that become available to creating what was an unprecedented clinical and biologically annotated clinical database, which provided a litany of insights in the prevention, treatment, and biology of major diseases, including cancer, cardiovascular disease, among many others. And the output of these studies has been extremely prodigious. But one has to realize, given the technology of the time, that we may be skimming the surface in terms of the potential discoveries that these databases of hundreds of thousands of individuals, and we know now there's other studies ongoing of millions of people, that we potentially could be missing things because of the current technologies we use. And I think with the proper application of AI and machine learning, and with the proper validation, one could generate new discoveries from these unique databases. At the same time, academic medical centers and healthcare organizations are sitting on a treasure trove of clinical and biologic data. We know that, and it is largely unutilized. And the focus of this slide actually was, the origin of it was a slide that I created in 2017 when I was leading the Cancer Center at Yale. And I think what's important is that we want to ultimately achieve the promise of what you can do with the vast data that healthcare organizations have to improve care and to improve our understanding of medical science. This is a truly untapped opportunity. I think part of what we'll hear this morning is the Nobel Prize winning work in protein chemistry that has enormous power in terms of drug discovery and understanding what polymorphisms do to the phenotype of proteins in patients, to look at the protein-protein interactions and how we can in fact create new, potentially undruggable targeted therapies, and as well engineer proteins for medicine and science in general. An incredibly powerful opportunity that AI, which was recognized by the Nobel Prize, is now generating. And at Genentech, where I work now, we are leveraging the growing knowledge of human biology, the massive scale and resolution of the experimental data that we're now generating, somewhat in part described by Dr. Getz a moment ago, as well as the vast inventory of therapeutic modalities that we have in our armamentarium at Genentech and Roche in conjunction with AI and machine learning in terms of ultimately identifying new targets and new therapies in a process that my colleagues at Genentech refer to as lab in a loop. And we think these technologies that you've heard from Dr. Getz and you'll hear from others today really have the opportunity to accelerate our ability to deliver unique, precise, effective therapies for cancer patients in need. But you know, yet another great opportunity is in the world that I live in now, which is R&D and clinical drug development, particularly oncology. And you know, the challenges of this space are renowned, they're well known, which is it takes too long, 10 to 12 years from the time a new molecular entity is put into initial trials, initially identified, to FDA approval. Tremendous costs, $1.4 to $2.4 billion per new molecular entity. We know that we're increasingly relying on precision medicine using biomarker-targeted populations, which increase the complexity and cost of clinical trials. As well, we're putting an increasing burden on our clinical research sites because of the complexity of our studies, the number of endpoints that we require, the extensive patient assessments, and as well, we ask them at site activation to use a series, multiple systems to collect data, record data, analyze data, and deliver data to the sponsor. And then finally, because of all of these opportunities, the demand for patients is growing and the pool is finite, and as well, the workforce at these clinical sites is actually shrinking. And so we must develop greater efficiencies if we're going to deliver novel therapies in real time. And I think AI has here a number of potential solutions in terms of better identification of what is the indication we should make for this particular drug. What's the best target patient population? Combination therapy is the mainstay in oncology, so what is the right dose and combination that we can do to accelerate into registration study? And what is the best endpoint for that study for both our understanding of the effectiveness of the drug, but also for regulatory approval? When we begin to start to think about conducting the trial, right now the process of selecting sites is you send a questionnaire to the site, they fill it out, you hope they filled it out accurately and honestly, and you guess, is this a site I should have? The data for what these facilities are doing is widely available, and through artificial intelligence, we could figure out what are the best sites to get a study done efficiently and quickly. As well, when we write protocols, a manual process, given the vast library of clinical trials and data, these things should be automated such that we're creating a fit-for-purpose protocol that efficiently achieves what you want and what you need to know to get a drug approved. And also that study builder could be designed in a way so if you tweak the eligibility criteria, you change the schedule assessments, you change other features, you know what that change will do in terms of the enrollment, the cost, the statistics, the ability to get it done. And all of this should be easily designed through various systems and artificial intelligence. As well, with artificial intelligence, when that protocol is written, you should be able to automate what are the data forms. Also, how do you conduct data review? How do you clean the data at sites? How do you manage the queries that go on with these sites? All manual processes that we should be eliminating through artificial intelligence and machine learning. And then lastly is the complex process of regulatory authorities, both from the initial IND to approval. One could use AI to say, how can I predict what would likely be the feedback of a health authority, the EMA, the FDA, and how do I address it before submitting? Also, how do I generate all these documents, clinical study reports, dossiers, in a way that reduces the workload of my people and ensures that we have an accurate and effective document for submission? And ultimately, I think all of these technologies are the levers for improving research and development in biotech and biopharma. Namely, the discovery efforts that you're hearing about can increase the number of new molecular entities that get into research, as well as, if they're designed more efficiently, more effectively, the value of those in terms of, well, return on investment, as well as improving the outcome for patients, increases. As well, if we design the processes and the trials in the way that I mentioned, we can increase the probability of success. To be clear, right now for an oncology drug that goes into phase 1 investigation, the likelihood that's going to be an approved drug is well under 10%. We have to figure out how to make smarter bets, and these technologies can do it. And then finally, in terms of efficiency, we know all the things that I described and more can reduce the cycle time, the time it takes to get from phase 1 to registration, as well as reduce the costs, such that for biotech and biopharma, you improve the return on investment, and most importantly for patients, you accelerate the opportunity to get important therapies to those in need. So in sum, I think, it's a really exciting time. You heard from Bill and others about the personal stories, because the fact is we know cancer affects all of our lives, whether it be our friends, our family, ourselves. And this is the greatest challenge, I think, in medicine of the 21st century. But I think the excitement of what we're talking about today will accelerate our ability to make a difference in the lives of these patients. And thank you for listening and giving me the opportunity to share some perspectives.